Equation of a line in 3 dimensions. Okay. Imagine a line in a space which is determined only when we know the direction, yeah, which it runs, and you need to know a point which is on the line. Okay, only then it can be defined as a line in space. So therefore, you have to also know the direction. So you need a point and you need a direction. So the direction is always the vector which is parallel to the line. Okay, and the vector is known as the position vector. So for example, if you consider the line L, this line L, which passes through point A, assume point A is x1, y1, and z1 because these lines are in 3 dimensions. So therefore, the coordinate for point A has to have x, y, and z respectively. Okay, and the direction vector, which is u, all right, it's a vector. So obviously, it's written in the form of I, j, and k having coefficients attached to it, A, B, C here. Okay, and point P is x, y, z. It can be any other point on the line. Right, so considering this, if you need to find equation of a line, I will explain in the coming slide how do you actually determine it. So provided you have a point and you have a vector, which is the direction vector for the particular line. Okay, so following up from the previous slide, all right, considering the same point that we discussed in the previous slide. So the magnitude of AP is obviously TU because T is in scalar form and U is the vector. So therefore, if AP is TU, right, then obviously P minus A, because AP is P minus A, equals to TU. So we are taking P in terms of A and T. So we just move the A to the right. So P equals to A plus TU being equation 1. If you write it out in component form, it becomes this. Right, so for the respective x, y, and z, it equals to A here is represented as x, y1, and z1. That is point A, right? x1, y1, z1, plus with the scalar t, right? Multiplied with A, B, and C respectively. Okay, because A, B, and C are the coefficients of the vector u, right? So vector u is ai, bj, and ck, right? So the coefficients of u are a, b, and c for the vector. That's how this value came about. And if you calculate each of the component, it becomes x plus at, y plus tb, and z plus ct respectively. So this will actually give you, so from this point, x equals to x1 plus at, y equals to y1 plus bt, and z should equal to z1 plus ct. So we are taking this equation as equation number 2. And in this case, the third equation is by making t as the subject for each of the equation in number 2. So what we are doing here is we're making t as the subject of the equation. So in order to make t as the subject of equation, you simply need to move around the unknowns. So you want to make t as the subject of equation for each of this equation 2. So t will simply be x minus x1 divided by a. Right? Same goes with the t for second equation of y. So it will be y minus y1 divided by b, and same goes with z. It will be z minus z1 divided by c, and we are getting t as a constant. So this is our third equation. Okay, now we are going to see 3 different forms of a line in a space equation. Yeah, so the first one is actually the form that has the vector attached to it. Recall back, the vector here is u. So the first form is known as the vector equation form of a straight line. The second one has a t attached to it. So recall back, we learned in chapter 1, equations that has t attached to it, normally we call them the parametric equation. So the system of equation in number 2 is known as parametric equation, and t is the parameter. So each x, y, z is actually expressed in terms of one parameter, which is t. That's why it's known as parametric form. The third equation is actually the standard form of equation for a line in a space. So it also has another name, which is known as the symmetric form or the canonical form. We use term of being standard and symmetric form more often than the canonical form. Okay. And these three terms or these three methods of writing the equation are interrelated. All right, and these are some key points that you have to understand. T is often omitted in symmetric form. Okay, this is symmetric form. All right, but it has to be inserted in other forms. You see over here, over in 3, you actually got rid of the T, but in the first and the second form, the T is always there. All right. And for the second point, if any of the value of ABC, what it means is ABC represents the direction vector. Alright, so if any of this is 0, so it's better to actually express your equation in the form of a parametric form. It's advisable, okay? And then for the third point, each point on L is uniquely associated with the value of the parameter of T. So it depends what the value of the parameter of T is. And then the value of x, y, z can keep on changing. So for example, if t is 1, then your x value will change. And then if a t is 2, then your x, y, z value will follow when t is 2 and it will be different. Okay, that's what it means by the third point. The fourth point says the equation of a particular line is not necessarily unique. All right, so for example, if you have these two equations and these two equations are in symmetric form, and you assume it should equal to t and make an assumption your t is 1. All right, if your t is 1 in this case, how are you going to identify what is the xyz value here? So it is stated here, is concluded that both equations represent a line that passes through a point 3 to 2. So how do we get the point? Okay, how to get the point? Okay, for example, the t value is 1. All right, I required you to assume it's 1, right? So x minus 1 over 2 should equal to 1. So your x value will automatically be 1 times 2 plus with 1, so it should be 3. Okay, same goes with the second value. It is y plus 2 over 4 equals to 1. All right, so how do you get the y? The y will simply be 1 times 4 minus 2, it should be 2. So the x is 3, the y is 2. So you have got your 3, your 2, and your z should be simply 1 by 6. All right, take away 4. Okay, by equating t to 1 for both equations. Okay, you can check for the second equation, you will also get 3 to 2 for the values of x, y, and z. So this is the point. So you see these two equations look different, but the point they go through is the same. And same goes with the direction vector, or it's parallel to the direction vector. So the direction vector in this case, how do we actually identify the direction vector value coefficients ABC? Remember, they are actually ABC at the bottom here. All right, they are the denominators. And these denominators can be simplified to achieve the vector value because it's a direction vector. So if you simplify it, it still represents the same direction. Okay, so 2, 4, 6, if you divide it by 2 for each of it, you will actually get 1, 2, and 3. So both these lines go through the same point, which is 3 to 2, and has the same parallel vector, which is 1i plus 2j plus 3k. Okay, now, if you need to write down the symmetric form of the equations of the line which passes through 1, negative 2, 8 and is parallel to 3, 5 and 11k. Yeah? So in this case, it's very clear. point 1, negative 2, 8, it's one of the point that the line passes through, and the direction vector or the vector which is parallel to the line is known as the direction vector. So direction vector here is 3i plus 5j plus 11k, and you're required to write down the symmetric form. So recap back from the previous slide, what is exactly a symmetric form? Okay, so a symmetric form here is a form that looks like that, right? Okay, so we will look at question A first. So how do we get? It's just by direct substitution. So remember, recap back, your A, B, C are the coefficients of I, J, K based on the definition of a straight line equation just now. So that's how you simply got your 3, your 5, and 11, your A, B, C. And x minus the point, it should be x minus x1, y minus y1, z minus z1. So in this case, your 1 here is represented by here, x minus 1. Your negative 2 is x minus negative 2, so it becomes positive 2, and it is your z minus 8. It becomes this. Right? So pay attention to the negative signs and so on. So it should be x minus x1, x minus y1, z minus z1. That's how you determine your symmetric equation of a straight line. So in conclusion, you need a point, you need a direction vector or a vector which is parallel to that particular line. Next, the question asked, does the point 2, negative 2, negative 7 and negative 3 lie on the line? So how are you going to identify this? When you have a straight line equations or when you have a quadratic equations, it's very simple. If you need to identify whether the point lies on the particular line or the curve, you just normally you substitute the equation, the points into the equation, and you prove that your values are equal, right, or consistent left and right. So but in this case, it's a symmetric form. So by substituting x, y, and z, you should consistently get the same t value. But this is symmetric form, right? So you should get same value of x, y, z. In order to prove, you should get the same value when you substitute your x, y, and z, which is consistent to a t value. Only then you can prove that a particular point lies on the line. So let's see how to do this. So for example, if you substitute your x as negative 2 into x minus 1 over 3, so you will get your answer as negative 1. And then you test it for your y, it will be negative 7 plus 2 over 5. And you test it for negative 3, it will be negative 3 minus 8 over 11. And you see consistently you got a negative 1, negative 1, negative 1. That is the t-value associated to this line. So therefore, since the results are consistent, negative 1, negative 1, negative 1, therefore the point lies on the line. Okay, now we are going to find equation of a line in a space where you are only given 2 points. You're given point A and B. So now remember, recall back, to find an equation of a line in a space, you need a point and you need a vector that's parallel to the line, or either you need the direction vector if it's given. Okay, so in this case, you only have 2 points. So you need to come up with your vector which is parallel to your line. How do we do this? We simply assume that the line has to be parallel to your line AB, right? Okay, AB, you assume is line AB because it passes through point A and B. So in this case, if you need to look for the vector that is parallel to AB, so the line must be parallel to AB. In this case, AB is always B minus A based on our basic definition. So B minus A, you minus each component respectively, and you get 1, 3, 2. So since the line passes through A, so we can also use point B, okay, but now we choose to use point A. So since the line passes through point A, so the point for A will be 2 will be your x1, your y1 will be B, and your z1 will be your 3. So it's x minus 2, y minus 1, and z minus 3. All right, over the direction vector. So we already found the vector that is parallel to line AB, right? So that is 1i, 3j, and 2k. So it is 1, 3, and 2 over here, and it should equal to 3. This is the symmetric form of the equation. Okay, and next, if you chose point B, you can also always choose point B. All right, so it will be x minus x1 will be 3, y1 will be 4, and z1 will be 5. All right, so it will be x minus 3, y minus 4, z minus 5 over the direction vector, which is 1, 3, 2. So bear in mind the direction vector does not change. The one you can change are the points in this case, yeah, and it should equal to t.